Chapter 9.1, Groups. So in this chapter, we're going to be exploring sort of the basis of algebra. We're used to having certain properties just work for us. Commutativity, associativity, distribution, those sort of properties are fundamental to our understanding of addition and multiplication, etc. But what we're going to look at now as we explore groups is kind of the question of, well, what do those things really mean? Why are they important? And what if they didn't work that way? So to begin, let's talk about mathematical systems. A mathematical system consists of a set of elements and at least one binary operation. So a binary operation is an operation or rule that can be performed between exactly two, that's where the binary comes from, elements of a set, such that the result is a single element. So addition, multiplication, subtraction, division are all binary operations. And the set of integers with the binary operation of addition makes a mathematical system, a system that we are very familiar with. So we have a bunch of properties that we, like I hinted at before, are sort of used to working, but let's look at them a little bit more in depth. So our first property is called the closure property. So if a binary operation is performed on any two elements of a set, and the result is also an element of the set, then that set is called closed or has closure under that given binary operation. So, for example, integer divided by integer is not always an integer, right? So if I take 20 is an integer, 8 is an integer, but 20 divided by 8 is 2.5, and that's not an integer. Thus, we say the integers are not closed under division. However, they are closed under addition, subtraction, and multiplication. Because if I multiply any two integers, remember integers being whole numbers including the negatives, so if I multiply any two integers together, I'm going to get another integer. Similarly, if I add two integers, I'm not going to suddenly get decimals in there, right? 3 plus 2 is 5. I didn't gain decimal places by doing that. So integers are closed under addition, subtraction, and multiplication, but not division. Then many mathematical systems have an identity element. So an identity element is an element in a set such that when a binary operation is performed on it and any given element in the set, the result is the given element. So the word identity here comes from essentially it identifies whatever it's operating with. So, for example, the additive identity is 0. Because anything plus 0 gives me back the original number, right? 2 plus 0 is 2, 3 plus 0 is 3, 17 plus 0 is 17. So it identifies whatever it's being added with. Then the multiplicative identity is 1. So anything times 1 is that number as well. 2 times 1 is 2, 3 times 1 is 3, 17 times 1 is 17. Anytime I multiply by 1, it's kind of like doing nothing. In the same way as adding 0 is like doing nothing, right? It doesn't change the number I'm working with. Once we have an identity, we can then talk about inverses. So when a binary operation is performed on two elements in a set and the result is the identity element for that operation, then those elements are said to be inverses of each other. So the additive inverse of a non-zero integer a is negative a, because a minus a equals 0. So 2 minus 2, 0. 3 minus 3, 0. 17 minus 17, 0. Now, this makes it sound like I'm changing operations, though. This is still the additive inverse. It's just that when we add a negative, it's like subtracting, right? So really what I'm saying is 2 plus negative 2 is 0. 3 plus negative 3 is 0. 17 plus negative 17 is 0. And then 0 is, in fact, its own inverse, because 0 plus 0 is 0. then the multiplicative inverse of A is 1 over A, because A times 1 over A equals 1. However, we do have to be careful that 1 over A may not be an integer, so most integers don't have a multiplicative inverse within their own set. We have to expand things a little bit. But if I'm in the set of real numbers or the set of rational numbers, then I get those inverses. 2 times 1/2 is 1. 3 times 1/3 is 1. 17 times 1/17 is 1. So there's always this way to get back to 1 or get back to 0. But notice that I can't actually, 0 doesn't have a multiplicative inverse. So that's something to think about when we get into our further properties, because there's no way to do 1 over 0, right? That doesn't exist. So that causes some problems. Next, we have the associative property. So for any elements A, B, and C within our set, if, parentheses, A plus B plus C equals A plus B plus C, or A times B times C equals A times B times C, then we have associativity. So in general, let's say we have the operation star. Like, we are going to use names of operations that are not just plus and times in the future. Like, we are exploring addition and multiplication because those are the ones we know, but the point is, when we study this subject, we want to think about it a little bit more abstract. So in general, associativity means, parentheses, A star B. So if I star A with B, if I do this operation between A and B, and then do it to C, versus doing BC first, and then A on the left, this gives me the associative property if these things are equal for all sets of 3 elements within the given set that we're working with. So, for example, let's just choose some numbers here. So 3 plus 5 plus 7. Okay, so that, using order of operations here, 3 plus 5, we do our parentheses first. So 3 plus 5 is 8, and then 8 plus 7 is 15. Versus 3 plus 5 plus 7 is equal to 3 plus, again, doing the parentheses first, so 5 plus 7 is 12. 3 plus 12 equals 15. So that doesn't prove that addition is associative, because we need to show it for any elements in the set, not just these 3, but for all of them. But addition is, in fact, associative, and that's something that we can just know, because some great mathematicians in the past have proven that this is just, in fact, true. It's how addition works. Okay, but a thing to think about now to remember this property is, why is it called this? What does associative really mean? So looking at this, it's talking about what our elements are associating with. So A and B are associating. If we think about the word associate, right, it means to, like, talk to, right? So A and B are talking, and then they bring C in. Versus B and C are talking, and then they bring A in. As long as that's the same thing in the end, it's still the 3 talking, right? Then we have associativity. They all can associate together, and it's the same thing. So that's where that name sort of comes from. Next, we have the commutative property. So addition and multiplication are, again, commutative. This means that A plus B is the same as B plus A, or A times B is the same as B times A, right? If I do 5 plus 3, that's 8, and 3 plus 5 is also 8. Similarly, 5 times 3 is 15, 3 times 5 is 15. So that's commutative. Commutative essentially means that they can commute with each other. Remember, your commute is like you're driving to school or work, that's your commute. You're moving, right? So you're allowed to move. So A and B, A plus B, B plus A, they're allowed to move. They're allowed to commute positions. That's where that name comes from. So in general, again, we want to look at this in the abstract. We're going to use operation star and say that the commutative property means that A star B, no matter what the operation is the same thing as B star A. Again, for all sets of 2 elements within our set. Okay, so now we have these 5 properties. What are we going to do with them? Because so far, most of the time, these are properties that we just sort of assume work, right? Because we're used to addition and multiplication having commutativity, associativity, all of that. And yeah, we've got some new definitions for inverses, etc. And, you know, closure might be an issue with integers under division and stuff like that, but addition and multiplication are pretty nice. But what are we really going to do with all these properties then? Well, we're going to look at a new thing called a group. So any mathematical system that meets the following 4 requirements, which we call the group axioms, is called a group. So if the set of elements is closed under that operation, if an identity exists under that operation, every element in the set, everyone has an inverse under the operation, and it's associative under the operation. Then we have a group. So again, we've explored certain systems that are groups, but we've also seen some that aren't, that break some of these rules. We also have a special type of group known as a commutative, also known as abelian group, which meets a 5th requirement of commutativity. So most of what we're going to look at in this class will meet that 5th requirement, but there are in fact groups that exist that do not meet commutativity. There are mathematical operations that you cannot do in both directions, right? We know this for subtraction and division, though those don't really meet the requirements for a group anyway. But not every operation is commutative, is something to think about. Which ones are and which ones aren't are very important. Now, let's look at some examples of groups, or maybe not groups. We're going to figure out how to show whether or not we have a group. So we want to determine whether the mathematical system consisting of the set of whole numbers, remember whole numbers being 0, 1, 2, 3, and so on, so not including the negatives, which gives us integers, under the operation of addition forms a group. So to answer this question, to answer any question where we are asked, is this a group? What we're going to do is we're going to go through the 4 axioms, and if it's asking, is it a commutative group, we go through the 5 axioms. So axiom 1 is closure. So we want to know, if I add any 2 whole numbers, do I get another whole number? The main problem here, we know 1 plus 2 is 3, right? 3 plus 7 is 10, and so on. I can't actually add every single pairing of numbers. There's infinitely many pairings that I can make. That's impossible to do. So in mathematics, to really prove something, we need to be able to show it rigorously, but for our purposes, we're just going to use examples where we kind of understand how these things work. So we can say that, yeah, when I add 2 whole numbers, I'm not going to gain any decimal places, right? It's going to still be at least an integer, but we just need to make sure, do I ever get a negative number? No, that's not going to happen either, right? No matter what, if I add any 2 whole numbers, it's still going to be 0, 1, 2, 3, 4, 5, one of those numbers. So we do, in fact, get closure. So the sum of any 2 whole numbers is a whole number. So it's closed under addition. Next, we look for the identity element. The identity element, since we're talking about addition, we already know what the identity element is because we have an additive identity by default. So the default additive identity is in fact 0. So we just want to know, is 0 in this set? And yes, it is. It's right here, right? So 0 is the additive identity. A plus 0 equals 0 plus A equals A for any whole number, in fact for any number where I'm adding 0. And since 0 is part of the set, we're good, we have that identity. And again, just like for the identity, we also have a default inverse element for addition. The additive inverse is the negative of any given number, right? So 2 plus negative 2, 3 plus negative 3, that's how we get back to 0. So are those numbers part of this set, this system? No, in fact, there are no negative numbers within the whole numbers. The additive inverse doesn't exist for anything except for 0 itself, because 0 plus 0 is 0, but there's no, if -1 is the additive inverse to 1, it's already broken. As soon as we are missing one element, our system is broken. 1 doesn't have an inverse, but neither does 2, or 3, or 4, or 5, or any of those. Since those negatives are not part of the set of whole numbers, we can stop checking our axioms. We don't have to go down to associativity. We can just stop and say, this system is not a group, because one of the axioms failed. All right, let's try another one. So let's look at the real numbers under addition. So real numbers, remember, those are all the numbers, negative, positive, fractions, square roots, pi, all of those numbers, all the real numbers, basically all the numbers we've talked about except for anything involving I, if you know what that is. Those are our real numbers. And then we're talking about addition, and we want to know specifically, is it a commutative group? So we're going to check 5 axioms this time. So first, closure. Question is, if I add 2 real numbers, do I get another real number? So if I add 2 real numbers, am I going to somehow get a non-real number? Have you ever added 2 numbers together and been like, that's not a number? No, of course not, right? So yes, we have closure. Next, the identity element. So again, we're talking about addition. We have the additive identity. We've already identified what the additive identity is. It's 0. So we just want to know, is 0 part of this set? And in fact, it is, because 0 is a real number. Again, any number I can name is a real number. Any number I can name that doesn't involve i's. Again, if you know what that means. So, 0 is the additive identity, 0 is a real number, so the system has this identity element. Next are the inverses, and so we remember what is the additive inverse. It's just the opposite sign, right? So 1, -1 are inverses, 2, -2. Pi, negative pi. Those numbers all exist within the real numbers, right? Negative numbers are real numbers. Negative pi is a real number, even though it sounds kind of silly. So the additive inverse exists for every real number, including 0 itself. So all of them have these inverses. We can always get back to 0 through addition. No matter what, no matter where we are, we can get back to 0. Associativity, this is one where we're just going to assume that it holds because we understand how addition works. We're not going to get into the proof of why this works no matter what, but you can assume that associativity as well as commutativity are going to hold for addition because I kind of introduced it in this way that this is a known fact that you're allowed to assume. Again, mathematicians don't like to just assume things, we like to prove them, but for our purposes within this class, you can just assume it. So we have associativity and commutativity, which means we have checked off all 5 boxes. All 5 axioms work out, and so this is not just a group, but a commutative group. So real quick, I'm just going to take a look at these practice questions just for a little bit of extra review here. So I want to briefly talk about the answers to these, even though this is really for your practice, but let's look at some of these examples. So integers under addition. Again, in this case, if I add 2 integers, so I'm including the negatives, the problem with the whole numbers was just that we didn't have the negatives, right? So yes, this one ends up being a group because we do have those negatives. How about rational numbers under multiplication? So we would think that this works out because the rational numbers include 2, 1/2, 3, 1/3, 4, 1/4. Those are each of our inverses. They have the multiplicative identity, which is 1. It's got all of that going for it. However, what breaks is, in fact, that 0 does not have an inverse, as I hinted at before. 0 there's nothing I can multiply 0 by to get to 1, 1 being the identity. So in fact, this one is not a group. Is a set of non-negative real numbers a commutative group? Under addition, so once again, no, it is not, because we're missing inverses, because the additive inverses are all the opposite signs, right? Is the set of positive real numbers commutative under multiplication? Now, positive real numbers means not 0. So we no longer have this problem of 0 not having an inverse, because 0 is not part of the set. And 2, 1/2, 3, 1/3, those are our inverses to each other within multiplication. So in fact, this is a commutative group under multiplication, even if it wouldn't be under addition. And then finally, it's a set of negative real numbers, a commutative group under multiplication. No, because it's not closed. As soon as I multiply two negative numbers together, I get a positive number. I've left my group. So, right, if I go -3 times -2, I'm now at +6. So I'm no longer in the negative numbers, and so I've broken my group immediately with the first axiom.